Okay, we're recording. So, good morning, everybody. Welcome back to Math 115. Let's see. How was everyone's weekend? Restful or stressful? I'm not feeling talkative today. That's okay. I'll share the screen and we can start. Everyone can hear me, right? Okay, there's some kind of issue. My chat is working on the iPad, but not on the laptop. Okay, 1 second. I'm going to rejoin the call on the laptop. Yeah, okay. Now I can talk. Alex Labrador, can you possibly mute your microphone? I think there's some feedback coming through there. Okay, well, sorry for the for the technical difficulties. I like these responses though. Rest and stress, bit of both. Banana daiquiri vibes. That one's not very funny. All right, cool. So, all right, we can start then. So, hopefully everybody turned in their homework on Friday. That was when it was due. The next homework is due this coming Friday. Okay, so they'll be due on a weekly basis on each Friday at 11:59 p.m. So that's the homework, which is in addition to your exit slips for the class, okay, which you need to fill out after each lecture. I think the easiest way to do the exit slips is to just watch the lecture and immediately do the exit slips. That's kind of how they're designed to be done. I do give the 1 week window though, in case people are watching asynchronously and they might be like a day behind or something like that, so they can do those exit slips within a week of each lecture. Okay, so what we're going to talk about today is more equations stuff, and specifically we're going to talk about how we graph equations. Okay, so we're going to start off by just talking about how we graph an ordered pair on the Cartesian plane. That's what we call this thing, which looks like a plus sign. We draw these arrows. We have the x-axis is the horizontal axis, and the vertical axis, we call that the y-axis. Okay, and we call this this parentheses a comma b end parentheses. We call that an ordered pair. and we call these numbers A and B, which are representing values in this case. We call those the components of the ordered pair. Okay, so we would call A the X component, and we would call B the Y component. Okay, and the way we graph them is just by setting up basically two number lines. In a crisscross fashion. And the X coordinate, the left one, we call that the X coordinate, is going to tell us how far left and right we go. And the Y coordinate is going to tell us how far up and down. Okay, so if we want to graph -2, 2, we should read the X coordinate as -2. That says we should go to the left 2. So here's -1 and -2, and then we should go up 2. So here's the point, let me do it with red. Here's the point -2, 2. And for 4, 3, all we want to do is move over 4, 1, 2, 3, 4, and then up 3. So that one would exist around there. Oops. Somewhere there. Okay, so that's how we graph ordered pairs. Okay, and we have a formula for how to find the distance between 2 points in Euclidean space. That's what we sometimes call this, or Cartesian space. So when we have a number line, it's pretty easy to find out how far apart two numbers are. You just count the numbers that are in between, right? So these 2 points, for example, would be a distance of 1, 2, 3, 4 away from each other, right? But when we have this this new coordinate space of going up and down, we have to revise our notion of distance somewhat. And the notion of distance that we choose is just the distance of the direct path between these 2 points. Okay, so we draw a straight line like that, and we imagine that as just a straight path, and we find its distance using the Pythagorean theorem. So we just would draw over a right triangle like this, and we would be able to count the distance, the horizontal distance here, on the X number line. So in our case, it's 6. And then we would be able to count the Y distance here. It's just going to be 1. So in our case, we would be able to find the length of this hypotenuse by using the Pythagorean theorem, and it would be given by the square root of 36 plus 1. So in other words, it's the square root of 37. Okay, and we have a formula for it. If you don't want to memorize the heuristic, the distance between x1 and y1. So these ones here are just to denote that this is the first point. And then x2 and y2, that's the second point. They're going to be square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared, units apart. Okay, so any numbers that I have, in our case, x1 and y1 were -2 and 2, and x2 and y2 were 4 and 3. And so that's how we would apply that formula. So that's one thing that you could memorize or put on a formula sheet for your exam or something like that. So we already sort of did an example, but let's have one more. -2, 5, and 3, -4. Oh, we're just going to do the square root. Why is x 6 and not 7? Probably I made a mistake. No, I think I got it right this time. So I just counted the number, like the distance here on the x-axis between -2 and +4. So we would count, it'd be 1, 2, 3, 4, 5, and 6. Yeah, so I think you might have somehow got these 4 and these 3 to make 7 somehow, possibly, or just miscounted a little bit there, right? But thanks for checking me, because sometimes I do get arithmetic wrong for some reason when I'm lecturing. Okay, so for this one, we're just going to subtract the x coordinates first. So we'll do 3 minus -2, and we'll square that. We will add -4 minus 5 and square that. And we get, let's see, this would be a 5 squared. So square root of 25 plus 81 should be -9 squared. So we add these two numbers, and what do we get? Like 106. And 106 could be 53 and 2. I think that's irreducible. Okay, so that's how we apply the distance formula. Any questions about finding the distance between 2 points? Yeah, Savannah brings up a good point. When you're counting these, the distance between 2 points on the number line, right? Like, for example, -2 and 4. What we want to count here are the spaces between. Okay, so we count each space, but not each tick mark. Okay, thanks for reminding me of that, Savannah. Okay, so that's distance between 2 points. We've also got another formula for the midpoint. I'm just going to give it to you. You just take the average of the x coordinates and the average of the y coordinates. So midpoint between x1, y1, and x2, y2 is just given by this formula. It'll be something like x1 plus x2 divided by 2, comma, y1 plus y2 divided by 2. Okay, some students get these two formulas mixed up, the distance between 2 points and the midpoint formula. But you'll always be able to tell whether you've used the wrong one, because they result in different things. If we take the square root of this for the distance formula, at the end we're going to get a number, okay? We're going to get a number, which distance is quantified by a number. So that makes sense. If we do the midpoint formula, it's going to give us a point. So if I ask, what is the distance between 2 points, and you tell me another point, I'm going to be very confused, because the distance should be a number and not a point, or an ordered pair. So that's one way that you can help keep them straight in your mind. Switch to blue. Okay, so we'll do an example. The midpoint between -3, 6. Okay, so what does it look like? It's like Negative 3, 6 is somewhere up there, and then 1, comma 4 would be somewhere like here. Okay, so we want to find the distance between these 2 points. This is 1, comma 4, or not the distance, the midpoint. This is negative 3, comma 6. Well, we just take each of these values, we take the x values and we average them. So average negative 3 and 1, we're going to get, well, if you sum them, you'll get negative 2, and then divide by 2, you get negative 1. And then we take the average of the y components, 6 and 4. The average of those two numbers is 5. Okay, so we should have negative 1, comma 5. That should be our midpoint here. Okay, any questions about the midpoint formula? All right, if not, let's move on. Okay, so now let's talk about the graph of an equation. Okay, so we've seen some equations so far. We've seen some linear equations, and we've seen some quadratic equations. We've even seen rational equations. Okay. And we've learned how to manipulate them algebraically so far. We learned how to add them, how to multiply them, how to factor them. And now we're going to talk a little bit about how to graph them. Okay, so if we have an equation, then the graph of that equation is just going to be the set of all ordered pairs, a comma b, which satisfy the equation. So we already learned how to graph ordered pairs, a comma b. We just move over left and right according to the a, and we move up and down according to b. So we just collect all ordered pairs, a comma b, where the b value, we plug it in for the y, and the a value, we plug it in for the x, and the equation makes sense. Okay, so for this one, what I would do is I'm going to just first take a second to consider the domain of this equation, which, remember, the domain is the set of possible x values which I can plug in, which make the right-hand side make sense. And x squared is going to make sense for any number that we plug into it. So x could literally be anything. So I'm just going to write down some random x values, and I'm going to plug them in and see what I get. So I'll try -1, 0, 1, and 2. Well, if we plug in -1, we'll get -1 squared would be 1, minus 3 is -2. And 0, we're just going to get -3. 1, we're going to get -2 again. And 2, we're going to get 1. So I'm just going to plot those on here. Okay. So we've got 0, -3. Got -1, comma -2, 1, comma -2, and we've got 2, comma 1. Okay, and you can just kind of use this method to try to fill in the gaps. Probably a lot of students in this class already know that this shape should be a parabola. So guided by that principle and the dots which you've drawn, you can just go ahead and fill that in like this. You do, in general, want to be careful about doing this kind of graphing, just because if we didn't have this additional information that we already know that this should look like a parabola, with this, there's lots and lots of ways which we could connect these points. For example, I could draw something which looks like this. Okay. So just be careful about filling in dots and saying that, okay, that is how this graph is going to be. You do generally need a little bit more information. In our case, we knew that the graph of this function should be a parabola because it's a quadratic equation. Okay, and quadratic equations always form parabolas when we graph them. Okay, so that's how we graph an equation. Okay, so what are X-intercepts? X-intercepts are points on the graph of a function such that the y value or y coordinate is equal to 0. So in other words, points of the form a comma 0. Okay, a comma 0, which satisfy the equation. Okay, and y-intercepts are going to be the reverse of that. They're going to be points on the graph of the function where x is equal to 0. So this would be points of the form zero comma b. Okay, so let's have a picture of what I'm talking about really fast. If I have some equation, maybe it looks like this. Then my x coordinates, excuse me, my x-intercepts are going to be points on the function such that the y value is 0. Okay, remember the y value is the height. Okay, so we look for the places where the y value is going to be equal to 0. That's going to be right here and right here. Okay, these are going to be x-intercepts. Okay, now you might be wondering, why on earth do we call them x-intercepts when their definition is that the y value is equal to 0? Okay, that seems confusing. But the reason we call them x-intercepts is because this is where the graph of the function intercepts the x-axis. Okay, the x-axis is what we call our horizontal axis. Okay, another term people use for this is horizontal intercepts. Okay, they say they're intercepts which intersect the horizontal axis. Okay, so we call them by the name of the axis which they cross when they occur. Okay, and then our y-intercept is just going to be where we intercept the y-axis. Okay. So that's how we define them graphically and have an understanding of what they look like. So let's have an example. So we have this function. We've got x squared minus x minus 2. Let's see how this factors. Well, we want a number which can, or we want two numbers which are going to sum to -1, multiply to -2. I think we can do x minus 2 and x plus 1. That should do the trick. So if we were going to graph this, we know these are the zeros of the equation. And maybe I'm getting a little bit ahead of myself, actually. Why don't we first, we'll leave this over here. Keep that in mind. Save that if you've written it down already. But first, let's talk about how to find an X-intercept and a Y-intercept. Okay. We solve for the X-intercepts by plugging in 0 for y. And we find Y-intercepts by plugging in 0 for x. Okay. So if we do the first option, and to find the X-intercepts, we would plug in 0 for y, and we would get 0 equals x squared minus x minus 2. And this is a quadratic equation with 0 on one side. So we can solve it either by factoring or by using the quadratic formula. In our case, we factor the expression on the right-hand side, and we can find the x values here, which cause us to have an X-intercept. Okay, and they're going to be the x values x equals 2 or x equals -1. So these are going to be the x values where we have an X-intercept. For the Y-intercepts, all we have to do is set x equal to 0. We get y equals 0 squared minus 0 minus 2. Well, that's just -2. Okay, so we get one Y-intercept. Okay, so if we want to take all this information and then it give us a picture based on what we've learned, okay, we would plug in X-intercept, which I'll draw those in pink again. It's going to be where our graph crosses the x-axis, and it's going to cross the x-axis twice. It's going to do it once at +2 and once at -1. Okay, and then we're going to have a y-intercept, which I'll do in brown, at -2. Okay, so if we were to fill in what this would look like, something like this. Okay. Again, I knew that it was going to have a parabola shape because the equation is quadratic, and quadratic equations always graph as a parabola. Okay, any questions about X and Y intercepts? All right, if not, then we'll move on. If you do have questions, don't forget I have office hours after class today. Okay, so now let's talk about symmetry. Okay, and by symmetry, I mean the same thing that we mean talking about symmetry when we talk about like someone's face being symmetric, right? If we think about somebody's face, well, what we can do is we can just divide it right down the middle, right? And the left and the right side are going to be mirror images of one another, okay? So when we're talking about symmetry in faces, we're kind of implicitly defining the reference point about which we assume the face is symmetric, right? When I say that this face is symmetric, I mean that it's symmetric about this red line here, okay? So meaning that it's symmetric on the left and right. I think it would look really funny if you had a face that was symmetric, say, about this axis. Then you'd have something really crazy going on, right? I don't know, maybe it'd look like this. Anyways, the point is that symmetry, okay, when we talk about symmetry, we need to talk about the reference point about which we are symmetric, okay? And so graphs of functions can have symmetry, and they can be symmetric about different points of reference, okay? So if we say symmetric about the y-axis, this is the sort of standard symmetry that you're used to, at least with this face diagram, okay? We mean left and right, okay? So about the y-axis, we mean something like this. That's not good. Something maybe like this. Okay, and what we mean is that for each point on the right side of the y-axis, we have a corresponding point on the left side of the y-axis with the same exact height and same exact distance from the origin. So this would be x, and this would be the point x comma y. And we have that negative x comma y is also a point on the graph. So the way we define symmetric about the y-axis is a graph is symmetric about the y-axis if x comma y and negative x comma y, how should I say this? Sorry, let me reword that a little bit. If for every point x comma y on the graph, negative x comma y is also on the graph. Okay. So we can flip the x coordinate of any given point and it will still satisfy the equation. Okay, so that's symmetry about the y-axis. Symmetry about the x-axis is similar. It's just that we're going to have things flip across the x-axis. Okay, so it's going to look something more like, I don't know, maybe something like this. Okay, and in this case, for every point x comma y, which is on the graph, we require the point x comma negative y to also satisfy the equation. Okay, so same deal as before, except we're gonna use x comma y and x comma negative y for that one. Okay, and the final one we have is symmetry about the origin. Okay, and it's going to be easiest if I just draw a picture of a function which is symmetric about the origin. We can draw this equation. The graph of that equation. And what we mean for this one is that for every point x comma y, we've got a corresponding point down here in the mirror dimension of negative x comma negative y. It's not so easy to read that. Negative x comma negative y. Okay. So for example, our example that we used here was y equals x cubed. You'll notice that for every point, if I do 1, 2, 3, my cubes are going to be 1, 8, and 27. Likewise, if I do -1, -2, and -3, my cubes are going to be -1, -8, and -27. So for each point 1 comma 1, for each point 1 comma 1, I also have the point -1 comma -1. For 2 comma 8, I've also got the point -2 comma -8, so on and so forth. Okay, so that's symmetry about the origin, and that's probably the one that I would expect most students to be unfamiliar with. Okay, so symmetry about the origin means we kind of, well, symmetry about the y-axis, we're flipping left and right. Symmetry about the x-axis, we're flipping up and down. And symmetry about the origin, we're flipping kind of diagonally. Okay? So that is symmetry about the origin. Any questions about any of these forms of symmetry? Okay, no questions. The nice thing about graphing symmetric functions is if we know a function is symmetric, all we have to do is graph one side of it and then copy it over to the other side of the axis of symmetry. Okay, so that's why symmetry is often useful. Okay, so let's ask the following question. Is y equals 1 over x squared plus 5 symmetric about the y-axis? Okay, remember, symmetric about the y-axis means that x comma y is a point on the graph implies that if we're symmetric about the y-axis, that means we'd be flipping left and right. So we should also have negative x comma y is on the graph. Okay, so if we want to check if this is true, all we have to do is take x and plug it into the function and plug negative x into the function. And if we get the same exact result, okay, then it's going to be true. Okay, so here's how we check. We check. Is 1 over x squared plus 5 the same thing as 1 over negative x squared plus 5? What do we think? Yes, I can upload the notes like week 1 notes. I'll upload the week 2 notes after this class. Let me write that down. Okay, so what do we think? Is this equation true? Is 1 over x squared plus 5 equal to negative 1 over negative x squared plus 5? Yeah. Bunch of yeses coming in, and it's true because if we take any negative number and we square it, right? We take some negative number and square it, we get the same thing as if we just took the positive number and squared it, right? Since, you know, -3 squared is equal to 9, that's the same thing as doing 3 squared, right? So yes, this is symmetric, and we can see the graph of it. This is what the graph of it looks like. Okay, so kind of comes up to this point right here, 1/5 is our Y-intercept, and just goes out from there. And each point that we see, which is on the right side of the y-axis, we have a corresponding point on the left side of the y-axis, which is the same distance away from the origin and has the same exact height. Okay? So that's symmetry about the y-axis, and that's how we would check that. Checking symmetry about the x-axis or about the origin is going to be the same thing. Okay, except we're gonna change this point right here where we say that xy is a point on the graph implies we might switch this -x comma y out for an x comma -y or a -x comma -y. But that's the only difference. Okay. So the last type of thing that we're going to learn how to graph today is circles. Okay, so we define what a circle is by saying that we choose some point in space, and I choose a distance r, and I define the circle to be the set of points which are exactly r units away from this point in any direction. Okay, so it looks something like this. So if I start standing here and I walk r units in any direction, the circle is what I call the set of locations which I could walk to if I walked r units away from where I am right now. Okay? Or it's like the set of points for which, you know, if you had like I don't know, some kind of, okay, look, I'm not an artist, but this is a horse. If you had a horse and it was it was like on one of those you know, mills or whatever, right? It would be the set of points which it walks around when it's like trying to mill those grains or something like that. Okay, wow, man, I've never had to draw a horse before, so just ignore this. Okay, so that's the points that we have on a circle. Okay, and we call the center of the circle, the point in Euclidean space, we call it h comma k. Okay, so meaning that we are h units to the right or left, and then k units up and down. And we call the radius, which is that distance, we call it r. And if we want to quantify the equation, which is going to express all of the points on this circle, is going to be the equation x minus h squared plus y minus k squared equals r squared. Okay. And this comes from the following. If we take this point h comma k and we were to draw out the triangle of this thing, and we know that this is 5, or not 5, this is r here, then this distance here is exactly going to be, if this is the point x comma y, then this distance here is going to be x minus h, and this distance here is going to be y minus k. And we know that this is a right triangle, so it obeys the Pythagorean theorem. So these distances are going to obey the rule that the square root of x minus h squared plus y minus k squared is equal to the square root of r squared. And if we just square both sides, we'd get x minus h squared plus y minus k squared equals r squared. I guess we could have just started there, huh? Anyways, it's nothing but the Pythagorean theorem, and that's how we define this equation of a circle, and this is the form which we call standard form. Okay? So let's have an example. If we want to graph a circle, we just want to take these pieces of information here and interpret them. The right-hand side means r squared equals 25. That implies that the radius r is going to be equal to 5. And our center is going to be formed by negating these two values here. Okay, so -2, +3 are going to be is going to be our center. And the reason is our standard form equation has an x minus h here, an y minus k. So if I write y minus 3 and I find k by assuming that that is the expression for y minus k, then k should be the number 3. Okay. Likewise, if I have x plus 2, that's like I did x minus a negative. Okay. So that's where I get that -2 from. So I just go to that point. So 1, 2, 1, 2, 3. We go to that point, and then we count 1, 2, 3, 4, 5. That's going to be 5 units away. We'll count 1, 2, 3, 4, 5. That'll be 5 units away. And then we would just want to draw a circle. Well, that's not a very good circle, but there you go. That's better. That's what it would look like. Okay? Where this distance is 5 units. Okay. All right. So that's how we graph a circle. So we're out of time. I was going to do this last example, but I will save it for next time. If anybody has any questions, please feel free to stick around after class. I have office hours. And otherwise, have a good rest of your Monday and see you tomorrow. Yep, my pleasure. So Catherine or Shruti, did either of you guys have questions about the lecture today? Or about anything else?